So today is March 14. March is the third month. This is 3.14. So of course it's Pi Day. And as I've done in previous years, I want to show a method of how you can calculate a value for pi. And this time we're going to be doing it on a Raspberry Pi 5. So if you want to find out more, please let me explain. So in this video we're going to be calculating pi on a Raspberry Pi 5, and of course there are many different ways in which pi can be calculated. So in 2019 I did a video for Pi Day about the Nilacantha infinite series. Today we're going to be using a different method, but if you're interested in that one, go back and check out that video. Okay, so this year we're going to be using the Leibniz formula for calculating pi, and it's really simple. As it says here, so pi over 4, so a quarter of pi, is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and so on and so forth. So it's really easy because after you do all these sums, you get a value for a quarter of pi and you multiply it by 4 and you get the value for pi. Also notice the series is really easy because it's a third, a fifth, a seventh, a ninth, so that's really easy to calculate, and it just flips between subtraction and addition, so no complicated formula to understand here. Some of the formulas for calculating pi can be a bit dizzying. This is really easy to understand, and it's one of these formulas that the more you calculate, the better value of pi you get, and we'll talk more about that in a second. It's also worth mentioning that this sometimes has other names. In fact, it's been discovered by 3 different people. There was an Indian mathematician who discovered it in the 14th or 15th century, and then it was later independently rediscovered by James Gregory in 1671 and then Leibniz in 1673. So it's a sufficiently well-known formula. Now, an infinite series is a set of sums in an infinite sequence. That means there is no end to it, so it just keeps on going and keeps on going and keeps on going, not just to 1,000 terms or 1,000,000 terms. It's just there is literally no end. And infinite series have some different characteristics. Some types of infinite series converge, so they hone in on a certain point and they converge towards a number, and this series converges on the number of pi. Now, because pi itself is infinite, there is no end to it, and because this series is infinite, you're never going to get to the end of pi, but as you process more and more terms, do more addition and subtraction according to that formula, you're going to get closer and closer to a definition of pi. And there are some infinite series that diverge. That means they go off towards infinity, or they oscillate here and there without settling on any particular value, or they behave in other erratic ways, but they're divergent. You don't know where they're going to end up. So we can see here after 1,000 terms, so 3, 5, 7, 9, just keep going for 1,000 of them, then this series will calculate pi to be 3.1 and then 395. So obviously, you could round that up to 3.14, but it's not quite there yet. So 1,000 terms gives you something close to 3.14, but not there. After 5,000 terms, you get 3.141, so that's good. After 100,000 terms, you get 3.1415, so that's good. After 1,000,000 terms, you get 3.14159. And then you go to 10 million terms, you'll get 3.141592. And then you can keep going more and more terms each time to get closer, in terms of decimal places, closer to the value of pi. Now, the disadvantage of this is that it converges very slowly. Calculating pi to 10 correct decimal places requires 5 billion terms. So a lot of work there just to get 10 decimal places. And there are ways of speeding up an infinite series like this, but to discuss those is beyond the scope of this video. Now, one good thing about this infinite series is really easy to understand. It's just addition and subtraction. Now, addition, of course, is commutative, so 3 plus 5 is the same as 5 plus 3, so it doesn't matter what order you do them. And subtraction is anti-commutative in that 5 minus 1 is equal to the minus of 1 minus 5. So I don't know about you, but when I'm doing things on a calculator, if I type them in the wrong way and I get minus number, I just drop the minus and I know what it should have been if I typed the terms in the right way around. So if you're careful with the terms, you can actually make subtraction commutative, you can do them in any order. So that means with this, we've got the ability to do some addition and do some subtraction, and actually we can do them in any order that we like, as long as we're careful about the terms and the minus sign. And that means writing code for this is really easy, because it's just this plus this or this minus this, fairly simple to write. Now there is the 1 over part that we have to do, but that's the same for every term. So once we do 1 over something, then, and that's part of the calculation, that's the same for every single term. Now, since the order doesn't matter, and if we are careful with the signs, we can split this into multiple tasks. That means we can write a multi-threaded program. So that's what I've done. I wrote a multi-threaded program that calculate pi, because each thread can handle some part of that infinite series, and then we can bring all the results together at the end to do one final sum to work out what the value should be. And in this example, I'll just split it into 2 tasks, one that does all the additions and one that does all the subtractions. Now that's really easy, all the additions, all the subtractions, and you bring them together at the end to give you that final value. Now on a Pi 5, that means this will run on 2 cores, as it would on a Pi 4 and so on. So we can get it running on 2 cores. Of course, Pi 5's got 4 cores. If you were doing this on a different machine with more cores, then you could split this up to run on more cores by dividing up the sequence differently again. You know, you could start with 3 at one point and then go forward 1,000 terms and start another thread 1,000 terms later on. Bit of simple math there, but I've done it on 2 just to show you the principles. So there we go. This is a multi-threaded method for finding the value of pi. Now, because we're dealing with lots of fractions, 1/3, 1/5, 1/7, 1/9, and then on, you know, up to 10 million terms, we're going to need more precision, more accuracy in the numbers after the point, the dot, than you get in normal C. So I'm using the GNU MP, the GNU Multiple Precision Library. It's a portable library written in C for arbitrary precision arithmetic on integers, rational numbers, and floating point numbers. Open source, of course, been around for a long time, and I'll show you how you use that in a moment. So here is the do pi minus 1. There's a do pi plus 1 as well, but it's very, very similar. It's just it's doing addition rather than subtraction. And basically, if you look at the code here, what have we got? We've got these MPF. So that's the multiple precision floating point numbers. So that's part of that GNU library I was just showing you about. Okay, and basically we have a 1 over I, because that's what we're doing, 1/3, 1/5, 1/7. And basically I set that number up to be 1, then I divide it by the bit underneath, the I, and that gives us this number, whatever 1/3 is in decimal, whatever 1/5 is in decimal, and then we just subtract them from the previous term. So we keep subtracting just like that formula shows. And I do exactly the same thing in another function, but for addition. So you just keep adding them. And at the end, you'll get a sum. And then if you bring the positive, the additional one, and the subtraction one together, then we can work out the value of pi. And I'll show that here in this next slide. There it is. So what we do is we create 2 threads. One thread runs the minus bit. One thread runs the positive bit. We then wait for those 2 threads to finish. And at the very end, we add them together. We multiply by 4, and then we print out the value of pi. Pretty simple. Okay, demo time. Let's see this running on a Raspberry Pi 5. Okay, so here I am on my Raspberry Pi 5. I have the program here that I've got. This code is the do pi plus function. Very similar to the other one, except for notice it's got the add in it rather than subtract. Not very long piece of code. It's available in my GitHub repository, and we'll just run it here now. So the first 2 lines out are the result of the subtraction and the addition series, and then the last one is those 2 added together, multiplied by 4, so you get 3.14159. So there you go. And then the rest of the numbers are there, but they're not correct yet because it hasn't converged closer to the actual number. 100 million there, you can bump up that number higher and higher. Of course, it does take longer and longer to run. Okay, that's it. My name's Gary Sims. This is Gary Explains. I really do hope you enjoyed this fun little video. If you did, please do give it a thumbs up. If you like these kind of videos, then why not stick around by subscribing to the channel. Okay, that's it. I'll see you in the next one.